Great.
Okay. Okay, thanks everybody for coming to my talk. I'm excited to talk about tight limits of non-locality from non-trivial communication complexity. I'll be presenting some joint work that I did with Mary Wootters and Patrick Hayden at Stanford. And so, yeah, so it's been mentioned before that entanglement can strictly beat shared random coins for certain tasks, such as non-local games and distributed computation tasks. And these are the tasks that we're going to be focusing on in this talk. So non-local games, I'll just give an example of probably the most famous non-local game to describe how they work. So in the CHSH game, so there are two players, they're not allowed to communicate, and they each receive a uniformly random input bit, X and Y, and Alice produces A, Bob produces B. They're just output bits, and they win this game only if the AND of their input bits is the parity or the sum mod 2 of their outputs. Okay, so if we give these players access to classical shared randomness, meaning they can both view some infinitely long sequence of shared uniformly random bits, then they can win only 3/4 of the games that they play, right? So this is the average case success probability of 3/4. But if they use quantum entanglement, meaning they have access to lots of EPR pairs or just an arbitrary entangled quantum state that's bipartite, and Alice can measure her part and Bob can measure his part in whatever way that they wish, then they can do strictly better. They can win about 85% of the time. And so this is kind of a surprising feature of quantum entanglement. And we can plot it like this, where we have the win probability of this game, and the quantum coin, so to speak, beats the classical coin. Okay, so now let's talk about distributed computation tasks and communication complexity. So communication complexity was sort of introduced by the previous speaker. So in this case, it's different from non-local games because the two parties are allowed to communicate, but their goal is to communicate as little as possible. And the task is now that for a worst case input, so X and Y are now bit strings of length n, then Alice and Bob need to be able to produce, one of them needs to announce, doesn't matter which one, this is the output of some Boolean function f of x, y. And they need to be correct with a bounded probability of error for that worst case input for all n. And the minimum amount of communication that they need to get away and succeed at this task, that's called the communication complexity of the function. And here we're just imagining they're exchanging classical bits. Okay, so some functions have really big communication complexity, even when you have access to quantum entanglement, such as the inner product function mod 2. The communication complexity of that function is n, and it doesn't matter, yeah, even if you have quantum entanglement. But there are some correlations or resources you can imagine Alice and Bob having access to that would allow them to compute arbitrary functions with a constant amount of communication, even for this worst case input, right? And we call this condition trivial communication complexity. And just to be clear, this is not something that describes quantum theory. This is not something that describes our world or any kind of reasonable universe. And it seems almost absurd to even imagine a situation where Alice and Bob can compute arbitrary functions with a constant amount of communication. But nevertheless, there is a deep connection between non-local games and trivial communication complexity. And that's the starting point for our work. I mean, it's kind of natural that there should be a connection because non-local games are almost like a special case because of trivial communication complexity, where the amount of communication is exactly 0 bits. So it was shown by Broussard, Berman, Linden, Miteau, Tapp, and Unger that communication complexity becomes trivial for two players who can win more than about 91% of the time at this CHSH game that I showed earlier. So on that chart before, if we have the classical coin on the left and then the quantum coin doing strictly better, there's this red zone up here where if we had some strange superquantum correlation that could win, say, 95% of the time at this game, then Alice and Bob could use that correlation to cause communication complexity to be trivial. So this in some sense explains why is the quantum win probability not 95%, or in general, why is it strictly less than this number, 90.8%? But yeah, so a better way of understanding this result comes from viewing Alice and Bob's behavior as a conditional probability distribution, the probability that they output A and B, conditioned on receiving the inputs X and Y. And if the inputs and outputs are all bits, then this is just some vector of 16 real numbers. So this is a kind of simple object, regardless of what the underlying mechanism is that they're using to sample from that distribution. So if we think about the reasonable sets of distributions, probably the only distributions that we're interested in are the distributions that do not allow them to violate causality. And we call that set the non-signaling polytope. So this is the set of conditional probability distributions which satisfy the added constraint that they cannot be used to signal information from Alice to Bob or Bob to Alice. So for example, this rules out a correlation where B is just equal to X, because that would imply that Alice's input X was signaled to Bob's output B, right? And any physical theory that is compatible with causality must only produce correlations that live inside of this polytope. It's not actually, strictly a box, but it's like a polytope of some dimension. And so inside of this box, we have two such physical theories that are causal. We have quantum correlations in blue and classical correlations in gray. So the set of classical correlations is also a polytope, but quantum correlations are not a polytope. They bulge out in various places beyond classical correlations. And this is what gives them their power to beat classical strategies at certain non-local games. In fact, non-local games like the CHSH game just correspond to different directions in this space of distributions. And the distance that you can travel in that direction while remaining inside of a set of correlations just tells you what is the maximum success probability that you can get at that game while using correlations from that set. So we can see that the best classical strategy is going to do no better than 3/4 win probability for the CHSH game. And then the quantum strategies do strictly better. But we can also see here, it's illustrated that if we use a non-signaling strategy, then we can remain inside the non-signaling polytope, meaning we're not violating causality. But we could, in principle, win the CHSH game every time, so with probability 1. And it was shown by Van Dam and independently Cleve that right at this point, at the tip of the non-signaling polytope, if you could win the CHSH game with probability 1, then communication complexity would become trivial. And then this was extended by Broussard et al. In the work that I just mentioned to this whole red region. So this means anywhere, if you had any correlation in that red zone, then you would cause communication complexity to be trivial. All right, and this will be useful for later, but this question remained, a very natural question: what happens in the intermediate region? So if you are slightly super quantum at this game, say maybe you win 87% of the time at the CHSH game, but not quite 95%, then what happens? And so we took aim at decreasing the minimum of this red zone from 91% to something lower. And what we noticed is that the proof of Broussard et al. Used this fact implicitly that formulas of noisy AND gates and noise-free parity gates or exclusive OR gates support reliable computation as long as epsilon, the noise on the AND gates, is less than 1/6. And we gave a tight upper bound that limits this approach. So we showed that the exact noise threshold for reliable computation by formulas of noisy AND gates and noise-free exclusive OR gates is 1/6. So this doesn't mean that you cannot possibly decrease the minimum of that red zone all the way down even to the quantum value, but it does cast some doubt on extending the proof strategy of Broussard et al. You would need to use a more generalized class of strategies, perhaps not using formulas, but circuits, or finding some other way to use these correlations that beat quantum mechanics at the CHSH game. So because this might be difficult, right, in light of this result, you may wonder if there's some other non-local game for which any super quantum success probability causes communication complexity to become trivial. And we answer this question in the affirmative. And in order to explain how we did that, I'm going to switch gears from this context of trivial communication complexity in non-local games to the setting of noisy circuits, fault tolerance of noisy gates, and amplification. And we'll see how these two areas are closely related. This will allow us to construct this non-local game. All right, so let's talk about logic gates. So here are 3 gates: the AND gate, the parity gate, and the NOT gate. And a basic question is, can you compute an arbitrary function using some formula out of these gates? And of course you can, because this is a functionally universal set of gates. In fact, you could have just used the AND gate and the NOT gate. Those would have been enough. So let's add noise. So we're going to add this noise parameter epsilon to the AND gates and tau to the parity gates. So this means that with probability epsilon, each AND gate will fail and return the incorrect bit. And similarly for the parity gates. And otherwise, they return the correct answer. And we're not going to add any noise to the NOT gates. Okay. So the analogous question to before is, can you compute an arbitrary function with a bounded probability of error for a worst case input using some formula out of these noisy gates? And of course, the answer is that it depends on what are exactly these values of epsilon and tau. So here's what was known about how it depends on epsilon and tau prior to our work. So we have epsilon, the noise on the AND gates, is on the horizontal axis, and tau, the noise on the parity gates, is on the vertical axis. So you can see that there's a region for very small values of epsilon, which extends for arbitrary tau. This is the red dotted region. So this was a construction of Evans and Pippinger, which showed that reliable computation is possible for arbitrarily noisy parity gates, as long as the noise on your AND gates is sufficiently small. And the reason is that, of course, the AND gate and the NOT gate are functionally universal. So if epsilon is really small, you don't even need to use these parity gates. But on the other hand, in this green starry region, a series of works by Evans and Schulman, Evans and Pippinger, and Falk-Unger ruled out reliable computation by formulas. So the interesting observation by Bressart et al., which was made implicitly in their work, is that in this yellow line segment along the epsilon axis, you can reliably compute, as long as epsilon is less than 1/6. And the question remained, could you extend the result to work all the way up to 1/4, which would correspond to bringing the lower end of that red zone all the way down to the quantum value at the CHSH game from before. So our result is this orange striped region of parameter space excluded. We showed that reliable computation is impossible with formulas in this parameter space, and in particular excluding this region along the epsilon axis for all epsilon greater than 1/6. And all that's left is this little box with the question marks. And I think that the techniques to fill in this plot are probably within reach. So hopefully someone will come along and show us exactly what this shape of the boundary is between regions of parameter space where we can reliably compute and those regions where we cannot. Okay, so I'll just mention two of the challenges that we overcame for our proof. So the starting point for the proof of this noise threshold of 1/6 is this argument that's due to Pippinger that shows that if you are going to try and compute arbitrary functions with noisy logic gates in these formulas, then you ought to be able to compute very simple unary functions that just depend on one input variable using arbitrarily deep formulas of noisy gates. And the way that this goes is, suppose you have some function that depends on all of its inputs, right? So imagine that this formula here supposedly depends on x1, x2, and x3. Then there must be some input such that the first occurrence of that variable is very deep in the formula. So here x1 has depth 1, that's not so deep. x2 is depth 2, that's not so deep. But we can find x3, which is pretty deep. And then we can fix some assignment of bits to all the other inputs such that the output of this function is either going to be x3 or not of x3. And that means that this formula needs to be able to propagate the information successfully from this one input variable all the way up to the output node. And then it's possible to show that if epsilon and tau are too large, then this is not possible. But this argument doesn't quite work in our case because we're not interested strictly in formulas. We were studying probabilistic mixtures of formulas. And this is because Alice and Bob have access to shared randomness, so they can execute probabilistic mixtures of strategies. So we were able to recover this intuition by showing that, in some sense, on average, the minimum depth of a variable like x3 is going to grow for some variable that the function depends on. Okay, so the other challenge that we had is that actually the argument breaks down. So the argument of Pippinger is that for functions that you can compute reliably with these very noisy gates, that they must depend on only a constant number of inputs. But this is actually false if you have noise-free parity gates, right? Because you can compute arbitrary parity functions with these noise-free parity gates. Those depend on all of their inputs, or they can depend on all their inputs. So what we did is we were able to reduce the case of the tau noise on the parity gates equals 0 to the case where tau is arbitrarily small but positive. And we used a structural result that derived from a connection with amplification that I'm going to present next. Okay, so in order to get that structural result, we needed a simple characterization of when you can reliably compute. So which noisy gate sets permit you to perform fault-tolerant classical computation with formulas. And in this context where we have these convex combinations or probabilistic mixtures of circuits, the answer is that yes, there is this very simple characterization. And it's in terms of amplifiers. So an amplifier is any circuit like the circuit C here, such that if you feed in independent and identically distributed bits, which are drawn from a Bernoulli distribution that's 1 with probability P, then the probability that the output of the circuit is 1 depends strongly on P about some fixed point. Here the fixed point is 1/2. So if you feed in, say, a 1/2 plus epsilon bias bit, you'll get out, say, a 1/2 plus 2 epsilon bias bit. And but if you feed in 1/2 bias bits, you'll get out a 1/2 bias bit. And this is, you can think of this as kind of like a noisy majority gate. You can use this to add redundancy in your circuit and perform fault tolerance so the error probability doesn't grow too large. And we would call this an amplifier away from 1/2. And we found that these objects are crucial because if you have a set of noisy circuits that's closed under convex combinations, then it allows fault-tolerant computation if and only if it contains both an amplifier away from 1/2 and a noisy NOT gate. A noisy NOT gate just means any NOT gate that is more likely to, in fact, flip the bit than not flip the bit. Okay, so if you have these two ingredients, you can reliably compute. And this was definitely implicit in prior work because, although going back to von Neumann, these works would add redundancy to their circuit using some low-depth circuit like C that acted as kind of a majority gate to do voting and error correction, right? But what's interesting is that you can actually go the other way. So if you allow for convex combinations of circuits, then if you can reliably compute, this implies that you have an amplifier away from 1/2. And then you get these nice properties like the case of tau equals 0 from before reducing to this case of tau arbitrarily small. But also this theorem allows us to construct the game that we want. Okay, so recall that we can describe Alice and Bob's strategy or their conditional probability distribution as just some vector in R(n). And we're going to imagine now that X and Y are no longer just individual bits. So this is just some high dimensional space. Okay, and remember that the directions in this space of different distributions correspond to different non-local games. And that if you travel too far in the CHSH direction outside of this quantum set, it's known that you'll be able to cause communication complexity to become trivial. So what we did is we were interested in finding a different non-local game like G corresponding to just moving in some other direction in this space, such that if you traveled by any epsilon amount outside of the quantum set, if you could beat quantum players by an arbitrarily small amount at this game, then you would be able to compute arbitrary functions with a constant amount of communication. And this is what we found. So our result looks like this red zone on the right, where it's some other direction, some other non-local game, where as soon as you leave this quantum set in that direction, you enter the red zone where communication complexity is trivial. And so in other words, we answered this question from before in the affirmative. And in fact, we found a series of games. So for each integer k, there's a non-local game gk, such that any win probability above the quantum value causes communication complexity to be trivial. But conversely, if communication complexity is trivial, then there must be some k such that the win probability for gk is superquantum. And so this game is fundamental among all such games in this sense. So it looks like this on this chart, where we have the classical players, the quantum players doing strictly better, and then any superquantum strategy would be in this red zone where communication complexity is trivial. So recall, just to see how we can construct this game, recall that Alice and Bob are just this distribution. And for example, the probability that they win a game is just some linear combination of the distribution entries, right? So this determines all their behavior. And what I'm going to describe now is a transformation from their distribution, from their behavior at some non-local game, into a gate, right? A logic gate doesn't have a sense of Alice and Bob. There are no longer two players. There are just inputs, and then there's one output bit, right? So, but the transformation is going to have the property that if Alice and Bob can simulate these correlations, then they'll be able to execute arbitrarily deep circuits of these gates with only a constant amount of communication. Okay, so if we have this Alice-Bob correlation, and we're just going to define the Alice-Bob gate to be on the same number of inputs as are given to each of Alice and Bob, right? And all the inputs and outputs are bits. So here, Alice and Bob each receive 2 input bits, x1 and x2, and then y1 and y2. So they're just going to be 2 input bits to this logic gate, z1 and z2. And the way that we determine what bits are given to Alice and Bob is we just choose them to be uniformly random, but subject to the constraint that x1 plus y1 equals z1 mod 2, and similarly for x2 and y2. So in other words, we distribute zi as these like linear shares mod 2 to Alice and Bob, such that neither party knows what z1 or z2 is, but if you were to bring their bits together, you could recover both z1 and z2. And then we do kind of the opposite for the output. So to find the output of the gate, we just take A and B, the outputs of their correlation, and we add them mod 2. And that's the output of the Alice-Bob gate. And you can see that this has this property I mentioned, that they can simulate arbitrarily deep circuits of these gates. Because if, let's say that the output of this Alice-Bob gate is the input, some Z1 prime for this next gate, then, well, we don't actually need to bring A and B together and add them up mod 2, because we're just going to split them back up again anyway into these linear shares. So we can just add a common uniformly random bit to both of them so that the distribution is the same. And then it's exactly the same thing, right? So in other words, like you don't need to merge them. You can just keep them distributed and continue until the very end. And at the very top of the circuit, you'll need to add the final bit output from Bob to the final bit output from Alice. And then you're done. So, okay, so this has this property that we want. And now we can define our non-local game gk. So for any integer k, there are 2k plus 1 input bits to each player. And these are drawn from some distribution, pxy, such that the marginal distribution on x is uniformly random, the marginal distribution on y is uniformly random, but they're correlated in some way. And they must produce output bits such that the parity of their output bits is the majority of the bitwise sum mod 2 of their input bit strings. So this you may recognize as of the class of games which are known as non-local computation games. So it turns out that if you choose this input distribution pxy correctly, then any win probability at this game that's above the quantum value implies that Alice-Bob, that gate applied to the correlation, functions as an amplifier away from 1/2. And there's also an Alice-Bob NOT gate. So for example, if Alice receives X, just flips it, applies a NOT gate and then outputs that NOT of X, and Bob just outputs Y as B, then that will flip the total sign of their parity of their shares. So there's a NOT gate in this circuit model. So that means that there's fault-tolerant computation by circuits of Alice-Bob gates by this equivalence between amplification and reliable computation. And they can also simulate arbitrarily deep circuits of these gates with a constant amount of communication, just using shared random coins. So that means that communication complexity becomes trivial for Alice and Bob. And I didn't mention this, but yeah, so because there's this other direction of the equivalence between reliable computation and amplification, if they have trivial communication complexity, you can show that they must win at one of these non-local games. And it's really not so surprising, right? They must be able to amplify these distributed bits. And so there must be some game, some k, such that they win GK more often than quantum mechanics. Yeah, so I'll just briefly mention, so in case you're aware, so non-local computation games, there's no quantum advantage for these games. So it's sort of unsatisfying because this game's quantum value is tightly limited by the axiom that communication complexity should be non-trivial. But the quantum value is the same as the classical value. So in order to rectify this, we noticed that you can just take a probabilistic mixture of this game with a pseudo-telepathy game like the Magic Square game. And this is just a game where there's a perfect quantum strategy, but no perfect classical strategy. And then if you imagine any superquantum set of correlations, then if it has a superquantum success probability at this mixture, then the only possible case is that there's a superquantum strategy at the game G in the first place. So that's just one of the tricks that we used. Okay, so here are some references, and here's the archive. I'll just mention that we posted this paper a few years ago with much weaker results, and then we just updated it. So that's why it has the old archive link. But yeah, thank you for coming to my talk.
Thank you very much, Noah. That was a really nice and clear talk. So please enter in your questions into the Slack channel. So we have a couple so far, one from Zohar. She's asking, I probably missed this, but how do the noisy gates lead to trivial communication complexity of Alice and Bob? I think this was earlier on in the talk.
Yeah. So yes. So in this CHSH game, what they're able to do is compute like the and of so I think what is being asked about is like, why is it so important that these noisy and gates along with noise-free parity gates support reliable computation? Yeah, so in the CHSH game, the output is like the and of x and y that's distributed as these linear shares, a and b. And if you use two instances of the CHSH game, then you're able to compute the and of two bits which are stored as linear shares. So if you imagine like you have x1 and y1, and you want to and that with x2 and y2, then there are two cross terms. And so you'll need to use two instances of the CHSH game. So if you can do those, if you can win each of those games pretty often, then you'll be able to perform this AND gate with pretty high probability. And that's what the mapping is between the CHSH game and these noisy AND gates.
And I guess if you want to like then carry out a circuit, you just sort of do this for every gate in the circuit.
Exactly. Yeah.
Thanks. So Harry Berman's asking, what's the ratio between the classical and quantum value of this new game?
So there are sort of two games. There's GK, as I defined it here, which is just a nonlocal computation game. So the ratio is exactly 1. But you can modify it by taking a mixture with a pseudotelepathy game, such that it has essentially the same properties, but where there's a quantum advantage at the game. So yeah, so it's a bit different from what you might expect, because it doesn't like naturally have this quantum advantage, but you can add it. Yeah.
And he follows this question up with, what's your guess for the original CHSH game in terms of whether the gap is still there?
This is an excellent question. So we noticed that, to the best of our knowledge, there's no circuit model of like classical noisy gates where circuits have a known to be higher noise threshold than formulas. So we conjecture that the noise threshold of 1/6 also applies for circuits. It's just more difficult to analyze. We could be wrong, but yeah, that's our guess. And then it is hard to imagine a different way of using these instances of the CHSH game, winning the CHSH game, to do something other than these noisy AND gates. But if somebody came up with a different way of using them, then that might be a route. And then there are other kind of things you can imagine, like maybe the reasoning, or maybe some argument goes like, you can use the CHSH games with quantum inputs or something, and then that's going to collapse communication complexity if you have super quantum success. But yeah, our guess is that after trying for quite a while and then proving this no-go result, it seems quite difficult to improve.
So let's see, let's try to sneak in one or two more questions. So Gibran Rashid is asking, does this rule out using majority over larger inputs for reducing the gap for CHSH?
So it rules out using a majority over larger inputs if you plan to, the question is, how will you compute that majority, right? Because you're going to have to use some AND gates. You can't compute majority just with parity gates. And if those AND gates are this noisy, right? If they're noisier than the 1/6 amount that was fine for Broussard et al., then you won't be able to write that majority as a formula. So formula is just you can write it as a circuit where there's no fan out. So every output only goes to one input. But our noise threshold only applies to formulas, right? And it shows you can sort of approximate a majority, but you're not going to be able to amplify. And that's what you need to be able to do.
Great. So maybe let's move the questions to the round table. And thank you to all the Noah and all the speakers of this session.